So the room is absolutely full of people, so we don't have room for anybody else. We have a limited admittance for restrictions, you know, and so in this case I think we are a little bit early on the schedule, but I think we can start with the scientific part. And the lecture of Professor Tao today is about asymptotic limits of polynomials and Sendov's conjecture. Please.
Thank you very much. This has been a very special experience. I don't think I've ever had a piece of art given to me before at a conference, but okay. So I'm going to talk about some work I did a year or two ago in a very classical area of mathematics, just the theory of polynomials of one complex variable, which you would think is a subject which has been completely understood, but there's still many open questions, even in this very classical topic. So I guess if we can advance to the next slide, please. Okay, so we're going to study very, very classical objects. Just take a function of a polynomial of one variable, which we call f of z. And let's make it nonlinear. Let's make it have degree n, and n is at least 2. So quadratic or cubic or higher polynomial. So we all know the fundamental theorem of algebra, that if you have any polynomial of degree n in the complex plane, has n zeros. And zeros I'm always going to write in red. Lambda 1 to lambda n are the zeros. Sometimes they may be repeated, and they can be ordered in any way, but they are always n zeros, and I'm going to call them lambda, lambda 1 to lambda n. But we can also talk about the critical points. The critical points are where it's not where the polynomial is 0, but where the derivative of the polynomial is 0, where you're stationary. So the zeros of the derivative. Now, of course, if f has degree n, then the derivative has degree n minus 1. So the critical points, which I will always express in blue using the letter zeta, there are n minus 1 of these. So for any polynomial, you have n zeros, and you have n minus 1 critical points, zeta 1 to zeta n. Again, they may be repeated. Now, we can normalize the polynomial to be what's called monic, which means that the first coefficient is 1. Then, of course, then we can factor. So the zeros determine the polynomial. You can write the polynomial as the product of n linear factors. And if you can go just move it a little bit, thank you. And the derivative is not monic, it has a factor of n at the front, but the derivative is also the product of n minus 1 factors coming from the critical points. So the zeros tell you what the function is, and the critical points tell you what the derivative is. Okay, and a basic question in the subject is, what is the relationship between the zeros and the critical points? How are they related to each other? So if I tell you what the zeros are, that tells you what the function is, that tells you what the derivative is, and that tells you what the critical points are. And conversely, if I tell you the critical points, that pretty much determines the zeros. I think there's one free parameter left. Okay, but what is the relationship between these two sets, if you like? There's a set of n points, n zeros, and n minus 1 critical points. And what is the connection? Okay, so there are many connections. So here is some numerics. I think this is a polynomial of degree 1000. And the way this was constructed was that you take the unit disk in the complex plane, you pick 1000 blue points at random. And then you multiply all the linear factors together, 1000 linear factors, you get a polynomial of degree 1000. Then you differentiate it, you get a polynomial degree 999. And you take the zeros of that, so you get 999 critical points. And those are the red points. And what you see, actually, sorry, the red points are the zeros and the blue points are the critical points, I think. Anyway, but you see something interesting when you do this experiment, that you see that that almost all the zeros, all the red points, are next to a critical point. So they almost match up completely. Every red circle comes next to a blue diamond. Of course, they can't all do that because there's 1,000 blue points and only 1,000 red circles and 999 blue diamonds. So that there has to be. So I think there's one circle in the middle that isn't close to a zero. But there is this very close. There does seem to be a very strong relationship between these two sets. Okay, can we go to the next slide, please? Okay, so what do we know about the zeros and critical points? So there are many classical results. So the oldest one, which you should all have learned as an undergraduate, is Rowley's theorem. So in the case where all the zeros are real, then we have a very simple theorem, that if all the zeros are real, then the critical points intersperse or interlace the zeros. So between any two zeros of a polynomial, if you have a polynomial with real zeros, so it's a completely real polynomial, between any two zeros, you have a critical point. Okay, that's Rowley's theorem, and you have n zeros, and so you have n minus 1 critical points. Okay, so they interlace. So that's a very simple relationship in the real case, but that's not true at all in the complex case. There's no notion of interlacing in the complex case. Okay, so next slide, please. Okay, but we do have kind of an analog of Rowley's theorem, which is also very classical and well known. It's called the Gauss-Lucas theorem. So the Gauss-Lucas theorem says that the critical points, wherever they are, they lie in the convex hull of the zero. So if you take the smallest convex set that contains all the zeros, it also contains the critical points. And it's actually quite easy to prove. The way you prove it is that you take the ratio of the derivative and the function itself. This is called the logarithmic derivative. And on the one hand, that is, you can write that in terms of the zeros, and it turns out to be just the sum of reciprocals of the zeros. It has a pole at every zero, but it has a zero at every critical point. So every critical point zeta is related to the zeros by this little formula, and just by playing around with some complex numbers, you can prove this Gauss-Lucas theorem. Okay, so next slide, please. Okay, so here is just a little depiction. If the zeros are these red points, then the convex hull is this polygon here, and the critical points lie inside this polygon. Okay, so that is the Gauss-Lucas theorem. What else do we know about the zeros and critical points? You can go to the next slide, please. Okay, here is one simple relationship. If you take all the critical points and you take the center of mass, the mean, you sum them all up and you average divide by 1 over n minus 1, that's the same as the mean of the zeros. So the zeros and the critical points have to have the same center of mass. That's not too hard to prove. You just expand out the function in terms of the zeros, and you expand out the derivative in terms of the critical points, and you compare the first two coefficients, and you just do a little bit of high school algebra, and you will see this relationship. That's another simple fact. The means are the same. Okay, next slide, please. Okay, now here is a much deeper theorem. This is called the perpendicular bisector theorem, and it was proved by Szego. If you have two zeros, lambda 1 and lambda 2, that are different, and you form the perpendicular bisector, you take the line between any two zeros, the critical points can't all lie on one side of this perpendicular bisector. They have to lie on both sides, or maybe on one side plus the boundary. So there is an additional relationship between the critical points and the zeros. It follows from another deep theorem called Grace's theorem, which I think I will skip. But I think the next slide has a picture. So maybe if we go to the next slide, please. Right, so if you have two zeros like this, this is the perpendicular bisector. So what can't happen is that all the critical points can't all be on one side of the bisector. They must be evenly spread. Okay, so this is an additional constraint between zeros and critical points, which is not covered by the Gauss-Lucas theorem. Okay, next slide, please. Okay, so now I can go to the main topic of this talk, which is this conjecture of Sendov. So Sendov did many explorations of zeros and critical points, and after a while, he found what he believed to be somehow the one of the sharpest statements you can make about the zeros and critical points. So if you put all the zeros in the unit disk, like we saw in the first numerical example, so if the zeros are all in the disk, then the Gauss-Lucas theorem tells you that the critical points are also in the disk as well. But we saw from the numerics that actually the critical points and the zeros should actually be quite close to each other. And the specific claim is the following, that whenever you pick any zero A, so any zero of your polynomial has to be close to a critical point. And the correct notion of close turns out to be unit distance. So for every critical point, so for every 0, there must be a critical point within distance 1 of the 0. Now this 0 could be anywhere in the unit disk, but the problem is rotation invariant. So you can rotate and you can assume that the 0 lies on the unit interval from 0 to 1. Okay, so next slide, please. Okay, so here is a depiction of the situation. So, this is a situation that cannot happen if Sendov's conjecture is true. So here's the unit disk. The red points are the zeros. All the zeros lie in the unit disk, which means that all the critical points lie in the unit disk as well. But what the conjecture says is that if you take any 0, like this one A, and you look at the unit disk centered at A, there has to be a critical point inside this disk as well. Okay, so this picture depicts a counterexample to Sendov's conjecture, where the critical points are actually they always stay a distance more than 1 from the 0. So this is a picture that should not happen. In this particular case, actually, this picture is ruled out for other reasons. For example, this picture doesn't obey the Gauss-Lucas theorem. The blue points are outside the convex hull of the red points. But you can construct other configurations which are consistent with Gauss-Lucas, but not with Sendov's conjecture. Okay, so this is the conjecture, and people have spent a lot of effort trying to prove this conjecture. You can go to the next slide, please. So why distance 1? So 1 is the best possible. So let me present 2 examples that show why this unit distance is the right conjecture. So here's a simple test case. So take this polynomial, z to the n minus z. That's a polynomial of degree n. So what are the zeros of this polynomial? Well, clearly there's a 0 at 0, so we'll call that A. But then there's also zeros in the unit circle. So there's the n minus 1 other zeros, and they're equally spaced on the unit circle. They're roots of unity. Okay, so the zeros of this polynomial are the origin, and then a whole bunch of points on the circle on the boundary, so that they all lie in the unit disk. When you differentiate, you get n minus 1 minus 1, and the critical points you can compute, they are also roots of unity times an additional factor, which is almost 1. So actually it's easier to just explain with a picture. So maybe the next slide, I think, has a picture. Right, so in this example, the zeros are all in the circle, and the origin, and the critical points are very close to the boundary. So this 0 is quite isolated. The distance between this 0 and the critical points is almost 1. So you can't. So the 1 in Sendov's conjecture cannot be replaced by, say, 0.9 or 0.99. So 1 is sort of should be the maximum, the most that the critical points can avoid, can be repelled from any given 0. So that is one key example that demonstrates this conjecture is almost optimal. Now I'll give you the next one. So next slide, please. So the other simple example is, so instead of z to the n minus z, take z to the n minus 1. So that's another polynomial of degree n. Now all the zeros are on the unit circle. In particular, 1 is a 0 of this polynomial, and then there are n minus 1 others, all equally spaced. But when you differentiate this polynomial, you get n times z to the n minus 1, and all the critical points go to the origin. So it's kind of the opposite situation for the previous picture. So in the previous example, all the critical points were near the boundary. Now they're all in the center. If we have the next slide, please, I'll show you the picture. Right, so here the zeros are all on the boundary of the unit circle, and then the special 0 is at 1. And then this big blue dot represents that all the critical points are on the unit circle. And so the distance from this 0 to the critical points, they are all equal to 1. And so here, Sendov's conjecture is completely sharp. You can't do 1 minus epsilon. You can't replace 1 by anything smaller. And so here, actually, so this is sort of the equality case of Sendov's conjecture. And it's conjecture that this is basically the only case where Sendov's conjecture is true, holds of equality, except for rotations and multiplying by a constant. Okay, so this is the conjecture. So what do we know about it? Okay, so next slide, please. If you fix the degree, so if you only work interested in polynomials of degree 7, say, then this is just a question about, so a polynomial degree 7 can be described by like 7 coefficients. So you just 7 zeros, 7 complex numbers, and that gives you the polynomial if it's monic. And this conjecture is basically some statement of some elementary inequality involving 7 complex numbers. And then you have to take derivatives and take zeros. You have to solve some algebraic equations. So it's, but it's a first order sentence in arithmetical complex numbers or real numbers. And there's an old theorem of Tarski and Seidenberg that any such sentence is decidable. So for any fixed degree n, you could even get a like Mathematica or some computer software to verify. In principle, the catch actually though is that if you use a standard algorithm, the time taken to verify this for any degree n is like double exponential in n. So in reality, actually, the conjecture has only been verified up to degree 8. Okay, so we know for polynomials of degree up to 8, the conjecture is true. There are papers floating around that claim 9 and 10, but they have not been generally accepted by the public in this, or by the community. Yeah, this, like many well-known conjectures, this one unfortunately attracts a lot of incorrect proofs. Okay, but it's true up to dimension 8, to degree 8. Okay, next slide, please. Okay, so that's the case of small n, small degree. Now, what about the opposite case of large degree? So there's a result of Bosana, Raman, and Sati about 40 years ago. If you make the disk, so you want to find a critical point inside the unit disk centered at A, the disk of radius 1 centered at A. If you make the disk just a little bit larger, then the conjecture is a lot easier. Right? For example, if you take the disk of radius 2, it's very easy, because in the unit disk, any 2 points are distance at most 2, triangle inequality. So you can replace 1 by 2 very easily. But it turns out that you can replace 1 also by the nth root of 2. So they show that given any 0, there's a critical point within distance 2 to the 1 over n. And as n gets large, 2 to the 1 over n is almost 1. So in some sense, Sendov's conjecture is asymptotically almost true. So one thing this tells you is that actually, even though the problem gets harder and harder as n gets bigger, after a while it might get easier and easier again. So the difficulty of the conjecture may somehow be have sort of 2 different regimes. So this is a hint that maybe the conjecture becomes easier as n gets very, very big. And in fact, there's a series of papers that were studying the large n limit, and we were able to establish various cases when n is large, but only under additional assumptions on this special 0a. Okay, so there's 2 parameters. There's the degree n, and there's this location a where the 0 is. And this location is anywhere between 1 and 0. And the location is very important. You see in the 2 examples that I gave, in one of the examples, the 0 was a was at 0, and the other example, a was at 1. So the 2 extremes of 0 and 1 are very important. And then there's also this intermediate regime where a is in the middle. Okay, but there's been a lot of results on all these cases, so we'll now go to the next slide and discuss some of them. Okay, so this is so a is somewhere between 0 and 1. Now, some cases are easy. So for example, if a is at 0, if a is at the origin, then the conjecture is easy, because at the origin, every point is within distance 1 of the origin inside the unit disk. So just from the Gauss-Lucas theorem already tells you that the critical points are in the unit disk, so they are certainly within distance 1 of the origin. So we can solve the case when a is 0. And you can tighten the Gauss-Lucas theorem a little bit, and Bojanov was able to show that the conjecture is true also for a up to about 1 over n minus 1. So for n very big, that's only a very tiny range, but there was at least some range where you can prove this. Okay, so that's what was known near 0. Okay, next slide, please. Okay, so near 1, conjecture is a bit trickier. So when a is actually equal to 1, It takes a bit of work, but several people in the 60s were able to show that this conjecture was true when A is 1. And then by refining these arguments using a lot of very careful Taylor expansion, actually, I think, yeah, so in the 90s, people were able to get a small neighborhood of 1, but they didn't, so they could get down to from 1 to 1 minus epsilon for some epsilon that depended on n. But the first few results didn't say what epsilon was. And then in 2011, there was a result that gave an exponentially small epsilon, and then this was improved to a polynomially small epsilon. So yeah, so the 1 minus 90 over n to the 1/12 times log n. Okay, so there's a little interval near 1 where the conjecture was also proven. Okay, next slide, please. Okay, and then there was some progress in the middle too. So there was a work of Degot about 6-7 years ago that showed that, and he used this Zagor theorem, this perpendicular bisector theorem, and many other tools. And what he showed is if A is bounded away from 0 and 1, so if it's between, it's bounded away from 0 and bounded away from 1, say it's between, say, 0.01 and 0.99. Then, as long as you're bounded away from both 0 and 1, then the conjecture is true as long as n is big enough. Then in the limit as n goes to infinity, he was able to prove the conjecture. In his argument, he didn't quite say what big enough meant, but this was worked out somewhat later by Chalegua. Okay, the precise bound is a bit complicated, but basically, for any n, he was able to verify this conjecture in a range which which is on the left is like constant over some power of n, and on the right is 1 minus constant over some power of n. And so as n gets bigger, this interval stretches towards 0 and 1, and that's why, as long as A is bounded between 0 and 1, eventually A will fall inside this interval as n is big enough. Okay, so it's so the conjecture was proved, for n big enough, the conjecture was proven near 0, near 1, and also between 0 and 1. But the whole thing was not, but we could not actually say the conjecture was actually proven for all values A because of these two gaps in this. The lower bound of this interval is bigger than the upper bound of this interval, and same over here. Okay, so the next slide. Okay, so yeah, so there are these two gaps that are missing. Okay, so I think I just said that, so maybe the slide after that, please. Next slide again. Okay, so what I was able to prove last year is that actually you can fill in these gaps, and there is some threshold, some degree, above which the conjecture is actually true for all choices of 0. Okay, so as long as there's some absolute constant n naught, such that if the degree is big enough, then conjecture is true. So that proves all the high degree cases of Sendov's conjecture. There's only a finite number of remaining cases to check. So in principle, this problem is now decidable. The problem is that this n naught is really huge. In fact, I don't even compute it. I can only indirectly show it exists. And computers can only get up to 8. So actually, the proofs actually are not computer assisted currently. So even though the conjecture is now in principle solvable, there's still a lot of work left to be done before we can actually finish off the conjecture. But it is at least in principle decidable now. Okay, next slide, please. Yeah, so the argument, it was actually inspired by arguments in PDE. Actually, a lot of things I do are inspired by arguments in PDE. It uses a strategy which I call compactness and contradiction. And it shows up a lot in PDE, which is where I first learned it. So if you want to prove something is true asymptotically, that some statement is true for big enough n, or in PDE, like if some statement is true if you're close enough to a blow-up time or something. Actually, Michael Struve uses this argument. I learned a lot of these tricks from him. If you want to show something is true asymptotically, you argue by contradiction. You assume that it's not true, and you assume that there are these counterexamples for bigger and bigger n. So assume that there's these polynomials of higher and higher degree that are counterexamples to this conjecture. Then you need to somehow hope that something is compact, okay? And somewhere within this sequence of polynomials, there's some subsequence that converges to something. Now, what converges means, we'll have to come to that. You have to choose the right notion of convergence in order to get a limit. But hopefully, these counterexamples converge to some limit. And often the limit is nicer than your original objects. They won't be polynomials. I will not reveal exactly what they are just yet. But they will have some nice properties. In particular, there will be some harmonicity properties that show up. And you can start using some tools. You can analyze the asymptotic limit using some tools that are not available when you're dealing with the individual polynomials. In particular, one of the key things I use is the unique continuation property of harmonic functions. So you study the limit and you get enough control in the limit that this tells you something about your original polynomials, and hopefully it tells you so much that you can get a contradiction. So this is a general strategy. Okay, so how does it work here? Okay, so next slide, please. All right, so let's try to start this strategy. Okay, so suppose that Sendov's conjecture is not true for sufficiently large degree. So if you work out what that means that there must be some sequence of degrees going up to infinity, n1, n2, n3, n going up to infinity. And for each of these n's, there is some polynomial of bigger and bigger degree. Okay, and so it has n zeros, it has more and more zeros in various places around the unit disk, and many, many critical points, also somewhere in the unit disk. And also we assume that each polynomial has a special zero, a. But it's a different zero, but as n changes, the zero will also change its location, but the zero moves around somewhere in the unit interval. Okay, so we have a polynomial, we have the zeros that are moving around, critical points moving around, and a special zero, which is bouncing around the unit disk. And so this is our sequence of objects, and we need to take some limit as n goes to infinity. And then hopefully get some contradiction eventually. So we assume that we have a counterexample, which means that if you take the unit disk around this special zero, there are no critical points. So all the critical points, they lie in the unit disk, but outside this other disk. So they lie in a loon, the region in one disk, but outside the other, another disk. Okay. All right. So the next slide, I think, has the picture of this. Okay, so now we have many, many zeros. Okay, and you should think of the number of zeros as going to infinity. We have one special zero, and all the critical points are trapped in this loon here. Okay, it's Luna in Italian. Okay, all right. Okay, all right. So now we need to somehow take a limit of all these objects. Okay, so everything depends on n. Okay, so really I should put subscripts of n everywhere, and you want to pass to a limit as n goes to infinity. All right, so how do you pass to a limit? So the easiest thing to do is the easiest object to take the limit of is a here. So if you take next slide, please. Okay, because we have one of the first compactness theorems you learn is the Bosana-Weierstrass theorem. Okay, if you have a sequence of numbers between 0 and 1, you can pass to a subsequence which converges to a limit. Okay, so you can throw away some of these polynomials, and you can assume that these a's converge to some limit, which I call a infinity. And that will also be in the unit interval. Okay, so for any finite n, a is a infinity plus something that goes to 0. I'll call that literal of 1. Okay, so the limit is so the a's will converge to some limit, and there are three cases. Either the limit is 0, the limit is 1, or the limit is somewhere between 0 and 1. The case when the limit is between 0 and 1, the result of de Gaulle I mentioned already takes care of that case, because if the limit is between 0 and 1, then a will eventually be bounded away from 0 and away from 1, and that case we already know we have a result. So really we just need to handle the two extreme cases, if a goes to 0 or a goes to 1, which corresponds to the two gaps you saw in the earlier picture. Okay. I think for lack of time, I will just discuss the case when a goes to 0. The two separate arguments that you need, they have some things in common, but I think I will just discuss one of them just to give you a flavor of the arguments. Okay, so next slide, please. Okay, yeah, so I was able to cover the two gaps. I was able to do two theorems, actually. One is that if a goes to 0 fast enough, so faster than 1 over log n, then you can get a contradiction. So I was able to basically resolve the conjecture in this regime. And then there's an opposite regime when if a is close enough to 1, you can also cover this gap here. But I think I'll skip that part and just talk about this result here. Okay, so next slide, please. Okay, so we've seen that the 0a we can pass to a limit, but what about these polynomials? Okay, so we have this sequence of polynomials. In order to make this compactness argument work, we need to find some subsequence of polynomials that converge to a limit. Okay, now what does convergence mean? Okay, so as you learn in your analysis classes, there's dozens of notions of convergence. Right? There's pointwise convergence, uniform convergence, convergence in measure, and whatever, blah, blah, blah. And if you try most of them, they give fairly silly answers. So for instance, this sequence of polynomials, z(n minus 1, this was one sequence of examples that was important. What is the limit of this sequence of polynomials? Well, you could maybe say, oh, let's try pointwise convergence. And these polynomials, their pointwise limits are kind of boring. Inside the disk, if z is less than 1, the z(n) goes to 0, and this just converges to a constant, minus 1. Outside the disk, z(n) goes to infinity, and so you have no limit. And on the circle, it goes round and round, it oscillates, and it doesn't have a limit, except maybe a 1. So you do get sort of a pointwise limit, but it's very degenerate. It doesn't tell you very much about about your function. And if you try other notions of limit, convergence and distribution or whatever, you don't get very interesting things. So it turns out it's not the polynomials that you should take the limits of. You should take the limits of the zeros and the critical points. But you have more and more critical points. You have more and more zeros. So how do you take limits in a compact way? So the idea is to think of them as probability measures, because there are some compactness theorems for probability measures. So this is a trick which I learned from the theory of random polynomials, and this is why I got interested in this question, because I was already working on the theory of random polynomials. But yeah, the idea is to think of the zeros and the critical points as probability measures, and those things you can take limits of. Okay, so let's take the next slide, please. Okay, so instead of taking all the zeros and all the critical points, consider a random zero. Okay, so out of the n zeros, pick one zero at random. And so this is a random point in the unit disk, or if you like, it's a probability measure on the unit disk. It's a discrete probability measure. It's just supported on n points, but it is some discrete probability measure on the unit disk, and so that's some of the zero measure. And there's also a critical point measure, so you take a random critical point, and that will give you some measure, a different measure on the unit disk. Okay, so for example, if you take f to be z(n minus 1, it turns out that a random zero would just be a random n through unity. So it's just a random point on the unit circle, and whereas all the critical points are at 0, so the random critical point is actually not random at all. It's always 0. So the zero measure is sort of a discrete measure on the unit circle, and the critical point measure is just the Dirac mass at the origin. Or if f is z(n minus z, then one of the zeros is at 0, and all the other zeros on the unit circle. So the zero measure is mostly on the unit circle, and this is a tiny bit of mass at the origin, but most of it is on the boundary. And the critical and the measure of the critical points is almost supported on the unit circle. It's supported on a slightly thinner circle than the unit circle. Okay, so we have these two measures. Okay, now why is this a better point of view? Next slide, please. Okay, so it's because we have a random version of the Bosana-Weierstrass theorem. It's called Procraft's theorem. So Bosana-Weierstrass says that if you have a sequence of deterministic points in the unit circle, in a unit disk, then there's a subsequence that converges. But actually, if you take a sequence of random points on the unit circle, so a sequence of probability measures on the unit circle, there's also a subsequence that converges. But the convergence is in the sense of convergence of distribution. So if you have a sequence of random variables, xn, let's say in the unit disk, and some limit, x infinity, we say that xn converges to z infinity in distribution if every test function of xi, the mean of any test function of xi n converges to the mean of the same test function tested against xi infinity. This is also the same notion as vague convergence in measure theory. For any test function xi, any continuous function. So that's the notion of convergence of distribution. It implies, for example, convergence of moments, that if you raise this to any power, the mean of xi into any k converges to the infinity to the k. And then there's a classical theorem Procraft that says that if you have any sequence of random variables that are supported in a bounded set, like a unit disk, then there's a subsequence that converges to a limit. Okay? So we can pass to a subsequence, and so we can assume that the random zero converges in distribution to some other random variable supported on the unit disk with some other, which I'll call lambda infinity, and the random critical point converges also in distribution to another random variable, which I call zeta infinity. So there are these two limiting random variables, and those are the correct objects to consider as the asymptotic limit. So you forget the polynomials, you only look at these two measures. Okay, so this is best illustrated by an example. If you go to the next slide, I think I have a picture. Not yet. Oh, okay. There are two examples. Okay, maybe skip this slide and go to the next slide. So I'll talk about this example using pictures. Okay. So if you take the polynomial z, I can do this now. Let's see how this works. Okay. All right. So. Oh no, that doesn't work. So I only have. Oh, that's there forever now? Okay. All right. Okay, so if you have this polynomial, the critical points, so for any fixed n, the critical points are all here. And for the, and the zeros are these it's a discrete measure on the unit circle. Okay. But as n goes to infinity, this discrete measure becomes more and more continuous, and in the limit, it converges in distribution to a uniform continuous random variable on the unit circle. So you just pick, just the Haar measure on the unit circle, or you pick a random point uniformly on the unit circle, and so it's these two measures are the limiting case. That's what the limit of this sequence of polynomials should be. Okay. I don't actually. Okay. So somebody cleared. All right. All right. So if you go to the next slide. Right, so if instead, okay, you have z minus z, then the zeros, you have one zero here and lots of zeros on the unit circle, but in the limit, this zero goes away because it's only density 1 over n. And the zero measure becomes just a uniform measure on the unit circle. The critical points are close to the unit circle, but in the limit, they converge to the unit circle, and they will also be uniform measure on the unit circle. So in this case, the two limiting measures are just uniform measures on the unit circle. Okay. All right. Well, this is what Art Week or something, so I have to. Okay. All right. Okay, next slide, please. All right. Okay, so why is it good to use these random variables? So it turns out that there's lots of really nice relationships between these random variables, which can be expressed using potential theory, and so this is where the PDE start coming in. So, for example, the fundamental theorem of arithmetic tells you that f is the product of your polynomial splits up into linear factors. So f of z splits up as the product of its linear factors. But if you take the logarithm of this, actually I take absolute values, I take reciprocal, I take logarithm, and then I take the average. You can rewrite this this formula as saying that if you take this particular combination of f, 1 over n log 1 over absolute value of f, that's the average of 1 over absolute value of z minus lambda, where lambda is now just a random zero here. So this particular function, which involves f, is determined by this random variable. So the random zero measure determines this particular expression. Now, this is an expression which is well studied in PDEs. This is called the logarithmic potential of lambda. It's the function whose Laplacian is basically the distribution of lambda times 2 pi, I think. And it's usually called u lambda. Okay, so lambda tells you what it tells you the log of the absolute value of f. And very similarly, the logarithmic potential of the critical measure tells you something about the derivative. So that's one relationship. Next slide, please. Another relationship is that if you take this same factorization and you take the logarithmic derivative and you normalize it, you get the average of 1 over z minus lambda 1, 1 over z minus lambda 2, and so forth. And so this particular expression, this normalized log derivative, is at any complex number z, is the expectation of 1 over z minus lambda. So this is also a very well-studied object. This is called the Cauchy transform or Stratos transform of this measure. And I'm going to call that S lambda of z. It's actually basically the derivative of this log potential u lambda. So there's another relationship that the Stratos transform of the zeros is this particular formula, and the Stratos transform of the critical points is similarly the log derivative of f prime. Okay, next slide, please. Okay, so a classical factor of potential theory is that if a sequence of measures converges, let's say complexly supported measures converges in distribution to a limit, then the log potentials will also converge locally in L1, but never mind exactly how it converges. But the log potentials will converge to the log potentials of the limit, and the Stratos transform also converges to the Stratos transform of the limit. So what you conclude, actually, is that in the limit as n goes to infinity, all these funny combinations of f and f prime, they converge to various potentials of the limiting measures lambda and limiting measure of zeta. So the limiting zero measure and limiting critical point measure tell you asymptotics of various normalized quantities involving f. So f itself doesn't converge to a nice limit, but these quantities converge to nice limits. But this would not have been sort of obvious unless you sort of took this probability theory, potential theory viewpoint. So, so knowing what these measures are tells you asymptotics, tells you useful asymptotics of f. Now we see that these quantities are also related to each other, so there should also be some relationships between these expressions here. In particular, the first three expressions here, they involve f and f prime, and so there should be some identity relating these three, and there is. So if we go to the next slide, please. Actually, this is an example, but I think I'll skip it. Okay, maybe next slide after this. Okay, maybe I'll skip that one too. Okay, that's just more of the example. So next slide, please. And okay, yeah, there's some more identities, but I think I'll skip that one too. Okay, so let's skip this this slide as well. Next slide, please. Okay. All right, I will come back to what I wanted to say. All right, so the first. Okay, so far we haven't done very much. We just took a limit and we used a compactness theorem. We used Procraft's theorem. But the reason why this is a good move, that you can actually say something, is because once you pass the limit, you can classify the limiting objects. And this is a standard trick useful on PDEs. You control the limiting object, and that tells you something about the original solution to whatever equation you're solving. So it turns out that you can work out almost exactly what these limiting measures have to be. So as I said, there are two cases, whether the special 0a goes to 0 or goes to 1. If it goes to 0, it turns out that both the critical 0 and the critical measure and the 0 measure, they both converge to the same measure, and they're both supported on the same set, which is actually a semicircle. And there's a similar law for the unit circle, but I think I'll skip that. But you can get a very strong control on these limiting measures, which gives you strong control on all these other quantities involving f. Okay, so I think there's a next slide which maybe describes what's going on. So next slide, please. Okay, so why is it good to pass the limit? Okay, so for any fixed n, as I said, we have these relationships. The log potential of the 0 is this particular expression involving f. The log potential of the critical points is this thing involving f prime. And the Stratos transform of the 0s is something involving f prime over f. So you can connect these three, and after a little bit of high school algebra, what you see is that there is an identity. The log potential of the 0s and the log potential of the critical points plus, so the log potential of the 0s is a convex combination of the log potential of the critical points and the log of the Stratos transform. This just comes by substituting all these identities. Okay, so this formula is not, doesn't look too scary, but it is a little complicated. But it gets a lot better in the limit as n goes to infinity. So if you send n to infinity, this goes to 1 and this goes to 0. And so now things get a lot better. So next slide, please. So this is what happens for any fixed degree. But if you pass the limit as n goes to infinity, you get a much simpler equation. And now there's an issue that this log sometimes is divergent. But okay, but in principle, you get a much simpler formula, which is that the log potential of the limiting 0s is the same as the log potential of the limiting critical points. Now, unfortunately, this term doesn't always go to 0. But this prediction is rigorous outside. It turns out to be rigorous for z outside the unit disk, not necessarily inside the unit disk. So basically, we have two measures, and their logarithmic potentials agree outside the unit disk. So that's what you can conclude. And this tells you a lot about these two measures. It tells you these measures that they're not quite the same, but they're very, very related to each other. They sort of look the same from infinity. They look the same on the outside, but maybe not on the inside. Okay, so what does this formula tell you? Okay, so next slide, please. So it tells you quite a lot. So once you know the log potentials are the same, you can conclude by Taylor expansion the moments are the same. You can conclude that the Stratos transforms are the same, at least outside the unit disk. Inside, they may be different. Okay, but there's a very nice interpretation using Brownian motion. I think that's the next slide. This relation actually has a very nice probabilistic interpretation. Okay, so you have these two measures. Oops. You have one measure for the 0s. No? Ah, I see. I don't have enough room. Okay, maybe the next slide, please. I don't have enough. Still no room. Okay. All right. Okay, so let's see what I can do. Oops. Where's my pen? Yeah, okay. Okay, here's unit circle. All right. So, okay, so I have this relationship that that these two log potentials agree outside the unit circle. So what this tells you, and another way of thinking about this is the following. So if you take it, so the 0s are distributed by some measure. Okay, so you pick a random point, you pick a random 0, and you do a Brownian motion. You do a random walk. Okay, on the units starting from a random 0, and eventually it will hit the boundary. So you take a random walk, and you get what's called the harmonic measure associated to this measure, and so you get some measure on the boundary. And then you can do the same thing for the 0s, critical points. You take a random critical point, and you take a random walk from a random critical point, and that will also hit the boundary eventually, and that will give you some other measure on the unit circle. And saying that these two log potentials agree outside the unit disk is saying that the harmonic measures of the zeros, harmonic measures of the critical points are the same on the unit circle. For those of you who know what a balayage is, it means that these two measures have the same balayage on the unit disk. Okay, but that is a lot of information, and it can tell you, for example, when a goes to 0, it tells you a lot. It tells you quite a lot. So if you go to the next slide, please. Okay. So yeah. So suppose a is going to 0. Okay. Okay. So remember, all right. So the critical points, they lie inside the unit disk, but they have to stay at distance 1 away from A. Okay, so so for any fixed n, the critical points are sort of stuck in this little loon, and A is going to 0. Okay, so in the limit, the loon gets compressed to a semicircle. So the critical points in the limit end up on the semicircle. Now, what about the zeros? The zeros are not compressed into this loon. The zeros could be all over the place. But in the limit, actually, the zeros also have to end up on the circle as well, because if there was some portion of mass in the limit, if there was some positive measure set of the zero measure, which was not in this loon, see, if you take a random Brownian motion from a point like this, there is some positive probability that it's going to end up on the right-hand side of the circle. But if you start on the left-hand side and you do a random walk, then with probably 1, you're going to exit on the left-hand side. So because of this, of the equality of the harmonic measures or balayages, you cannot have, it is not possible for the zero measure to have any mass at all in the limit in the interior, and so the measure also has to be the measure of the zeros has to also be on the same semicircle as the measure of the critical points. And in fact, in the limit, they're exactly the same measure. So this is how you can start using information. This is how you use this analysis in the limit. Okay, next slide, please. Okay. All right, this is the opposite case, but maybe I'll skip this slide. I think maybe, okay, maybe 2 more slides. I can skip this slide as well. And this one as well, okay. Okay, let's skip this one too. All right. Next slide, please. And next slide, okay, there's a reason why I want to skip this argument. I'm very fond of this argument, but it would take a bit too much time to explain it, I think. The other case, it uses a unique continuation quite a lot. Next slide, please. All right. So, we now know, at least when a goes to 0, we now know that the zeros and the critical points both converge to the semicircle. But how do you get a contradiction out of that? So that's where I'll finish. We use a tool from complex analysis, which is just the argument principle. How am I going to describe this? All right, yeah, maybe with the picture. Okay, maybe go to the next slide. Okay, so as I said, the zeros and the critical points are both moving to the unit circle. All right, so what we're going to do is that we pick a small circle around the origin, okay, so of radius, say, 0.1 or something. So it will also contain this A. So we have this little circle, and maybe I'll give it a name, gamma. And we have the Stratos transform, so the zero measure, so for any fixed n, you have some zeros. Okay, so for any fixed n, the zeros look like this, and then you get the Stratos transform, that's a rational function. And it will converge in the limit to the Stratos transform of the limiting measure, which is only on the unit circle. So what we're going to do is that we're going to take this, this curve gamma, and we're going to map it by S gamma. Okay, and that will give you some curve. Okay? And we're going to ask how many times does this curve wind around the origin? Okay? And the argument principle tells you that the number of times this winds around the origin is equal to the number of zeros of S lambda inside this disk minus the number of poles. Okay, so the winding number is the number of zeros of S lambda minus the number of poles. But what is S lambda? Okay, so S lambda, okay, it's if you actually it was the log derivative of f. So the zeros are actually the critical points. So yeah, so this function has some critical points over here. Okay, so these are the zeros of this function, and the poles are the zeros of f. So all the red dots are poles, and all the zeros are all the zeros of f are the poles of S lambda, and all the critical points of f are the zeros of F lambda. So this function has no zeros inside this circle because all the zeros are stuck on this loon. But it has at least one pole because there's this A here. So the winding number actually has to be negative, okay, because there's one zero, and so there's one pole and no zeros. There could be more than there could be more zeros inside here, but there's at least one zero. Okay, but on the other hand, if you this is converging to S lambda infinity, which is the Stratos transform of some measure over here, and that's holomorphic in this disk. Okay, so that limit has no poles and maybe some zeros. So in the limit, the winding number is actually non-negative because yeah, there's no more poles in here. There's only zeros. But S lambda is converging to S lambda infinity, and so that should give you a contradiction. Now, it's a little more complicated than that because winding number is not quite continuous but this is fixable with a little bit of effort. But so the end game is a certain amount of complex analysis and this resolves the case when A goes to 0. When A goes to 1, it's substantially more complicated and there's a lot of Taylor expansion. But I think I will skip that because I'll finish here. So thank you very much for attention.